discussing motions in the sky, and we talked about the diurnal motion, that's stars rising and setting due to the rotation of the Earth. We talked about the annual motion, the slight shift every day that stars have due to the motion of the Earth around the Sun. Then they combine these kinds of motions together, and you get the whole idea of timekeeping. And so we did that. But let's get back to motions a little bit. There's a couple other kinds of motion that exist out there that I want to talk about. One of them is in Chapter 2, and that is the idea of precession. So let me explain that first. So precession. Imagine you have a top, and the top is spinning, and it leans over. Well, most things, they lean over fall over, but tops don't do that. Tops kind of change direction they're pointing. They wobble as they're spinning, and that's because of how gravity pulls on them. They're rotating. The gravity exerts a torque on it. In physics, we learned that torque is related to change in angular momentum. It gets kind of complicated, but the end result is it changes direction it's pointing rather than falling over if it's spinning. And I have a demo I often do in class of this, in which I have something that's spinning, and I lean it over, and it wobbles instead of falling over. And so the Earth does the same sort of thing. It's a big spinning thing. We have gravity of the sun, the moon, and the planets pulling on it. And so rather than it changing and leaning over and changing the amount of tilt that it does, instead, what it does is it changes the direction that it points. And so that is called precession. And so here's kind of a graphic showing that as the Earth is turning, it's slowly changing where it's pointing in the sky. Now, it's turning much faster. It's precessing much faster in this animation here than it does in real life. In reality, it takes about 26,000 years to make one complete circle here. Okay, and so that's obviously takes way less than that in this animation. Right now, the Earth is the North Pole of the Earth is pointed at a star that in ancient times used to be called Cynosura, and it's the little end of the Little Dipper. That star we now call Polaris. In the ancient times, when they were building the pyramids, for example, in Egypt, Earth pointed at a different star altogether, Alpha Draconis, the star that we call today Thuban. So that was the North Star in the distant past. Now, what we have here is we've got the star that they used to call Cynosura is now the North Star, and so this changes over time. And here's a graphic that's from your book that shows, for example, the star Thuban was the North Star in the distant past. Now the Earth is pointing right next to the star Polaris, and technically it's not right at Polaris, it's right next to Polaris. So Polaris makes teeny tiny little circles in the sky over the course of the day. If you go out at night and look, Polaris is not a very impressive star in the sky. People often think that the North Star is the brightest star in the sky because you were often told that when you were a kid, but that's wrong. And I like to go out at night. One of our first labs, we'll go outside and I'll ask students, okay, can anyone point out the North Star? And everybody inevitably points to like whatever looks really bright. And I say, nope, you're pointing west. No, you're pointing south. No, that's southeast or something. And finally, it turns out that the North Star is a really dim little star that's actually kind of hard to see from campus. And that's just the way that it is. It just happens to be its north, and that makes it a very special sort of star to navigate by. Well, if you wait, maybe in about 10,000 years, Earth will be pointing real close to the star Vega. Vega is that really bright star that you see almost right overhead right now. But in 10,000 years, that'll be really close to the North Celestial Pole, and so that'll be a North Star. So if you want to see Vega as the North Star, you got to wait 10,000 years. I mean, not sure how you do that. I guess like on the animated show on Futurama, you know, you get your head cut off and stuck it in a jar and have it, you know, reanimated 10,000 years from now, and you can look up and say, oh, wow, cool, a really bright star is the North Star. Okay, but all right, so what you do is you shift all this, and the entire sky shifts. The North Pole is shifting, and I'll get back to that in a second as to what that does, because if you shift the North Pole, that's going to shift the equator. If you shift the equator, that shifts where the sun crosses the equator, so that shifts the equinoxes. Well, it also shifts where the sun is farthest north and farthest south. Remember, we talked about the Tropic of Cancer. That's the spot where the sun is farthest north. Can be that's place on Earth where the sun's farthest north. It's called the Tropic of Cancer because thousands of years ago the sun was in the constellation Cancer when it was farthest north. Now it's kind of between Gemini and Taurus. Calling it the Tropic of between Gemini and Taurus just sounds silly. The southernmost latitude is the Tropic of Cancer. Tropic of Capricorn. Tropic of Capricorn because the sun used to be farthest south in the constellation Capricornus. It's not anymore. It's really closest to farthest south, sort of between right along the edge of Sagittarius and Scorpius. And so that's the farthest south the sun gets. Technically, the sun used to be on the equator in Aries. It's not, in fact, they call the zero of right ascension, that's where they start all the coordinates, the first point of Aries, except it's no longer in Aries. It's actually shifted so that it's moved through Pisces and it's about to enter into Aquarius. So all that is shifted. Technically, whatever astrological sign you are is the constellation the sun would have been in if you were when you were born, except that precession has changed all that. One of the things I like to do with my nighttime students is we'll look up like on a horoscope or something. You know, the astrologers say, you know, that such and such, you know, is going to happen because Jupiter is in Leo, and we'll go out at night and look, and we see Leo in one part of the sky, and Jupiter is clearly in another constellation. And that's all because you were not born 2,500 years ago when all this was set up. Well, there's another kind of motion that's out there, and that is that the Earth wobbles on its tilt a little bit. That's called nutation. And it has to do with various things that are going on with Earth and the gravitational pull on Earth between the moon and the planets and the sun. The moon's orbit actually wobbles a little bit, and that causes the Earth's tilt to wobble. And so that if you change the tilt, that changes the latitude and longitude of the Tropic of Cancer and Tropic of Capricorn. And so a bunch of years ago in Taiwan, they built a national park right on the Tropic of Cancer, which runs right through the island. And they had this obelisk here so that at noon at the summer solstice, the sun would shine right down along the sphere, and there'd be a hole in it. It would cast a spot of light at the base of that opening right there. And it worked really fine for a number of years, except that the Earth changed its tilt a little bit, and so the Tropic of Cancer slowly moved until it was no longer even in the park. Now, this is not a permanent thing. It turns out this wobble goes back and forth, and there's several different cycles for the wobble, and so what actually happens is that the sun eventually gets back to the park, and then it gets off again, then it gets back, and then gets off again. and the Tropic of Cancer goes right through Mexico. And there's actually a physics professor down in Mexico that has taken up a deal in which he moves these markers showing where the Tropic of Cancer is in different years, and it shifts a little bit every year. And so again, that's an indication that the Earth does change its tilt ever so slightly, or what we call the inclination. Now, what effect does this have on us? Well, right ascension and declination, remember, zero of declination is the equator. The right ascension, the zero of right ascension, is supposed to start right where the sun crosses the celestial equator. So zero right ascension happens at the vernal equinox. Unfortunately, if you move the equator, because you move the pole, that changes the right ascension and declination of every star. If you change the tilt of the Earth, that's also going to change things, because that changes also exactly where the North Pole is and shifts the equator back and forth slightly. And so that means that the coordinates of stars keep shifting all the time. And so what you want to do is keep track of that. Now, it's very difficult to say, okay, every year it shifts a little bit. In fact, it shifts during the course of the year. And so how do you know what the right ascension and declination are? Well, frequently what you do is, like in a table of data or something, or if you look in a guidebook or a map that shows where things are, they show you where they are at a particular moment in time. And we call that the epoch, okay? And so the epoch of the map. So you would often have a map, and it would say what epoch the map is for. Sometimes it writes it as J2000.0, so that would be the beginning of the year 2000. J2000.5 would be midway, so that would be like it 1st of July in the year 2000. And so if you look on Stellarium, then you end up with an interesting sort of thing. And that is, there's two sets of coordinates for everything you click on. One of them is the coordinates that are calculated for the day that you click, and the other are coordinates for an epoch, either epoch 1950 or epoch 2000 or epoch 1900. Those are the common ones. And so there are times you want to know the coordinates relative to something like that, to an epoch, because sometimes when they give the location of something, they give the coordinates as if they were that epoch, and other times you want to know the coordinates right then and there. And so there are different times that you'd want each of those different coordinates, but they are both of them given for you in Stellarium, which makes it very important that if you're looking at something, in particular in one of our labs, the proper motion lab, you need to actually look at the correct coordinates. You need to read the directions for the lab, and it tells you which set of coordinates are the correct coordinates to use for that lab. Okay.